In this video, we will discuss exponential and logarithmic equations, which means we can be given y equals b to the x and or x equals log base b of y, and in any case, x, y, or b can be the unknown. So we need to look at some methods for solving for x, y, or b. And here are some guidelines that you can jot down. If you want to pause the video and write down these guidelines, that would be a good idea. So guidelines for solving exponential and logarithmic equations. Basically, use the two forms together, switching when it is helpful. So as I discussed earlier in this unit, it's very important to be able to switch forms between exponential and logarithmic form. And this is very helpful for solving equations. So number one, if the equation is in exponential form and x is the unknown, change to logarithmic form and solve for x. Number two, if the equation is in exponential form and b is the unknown, take the log of both sides and solve. You might need to change log form to exponential form later. If the equation is in logarithmic form and y is the unknown, change to exponential form. Note that before changing from log form, the coefficient of the log must be equal to 1. And therefore, you will have to apply one of the properties of logarithms that were discussed earlier. And number 4, if the equation is in log form and b is the unknown, change to exponential form and take the log of both sides, and you may need to convert back to exponential form again. So, we need to look at some examples to illustrate all of these steps or these different approaches in the guidelines. Example 1. If 3 to the power of x is equal to 18.381, how do we solve this to find out what exponent x works for this equation? And trial and error is not permitted. Okay, saying that with a smile. I know some people want to try that, but don't resort to trial and error. So what do we have here? We have an exponential equation where the exponent is the unknown. So I think it's the first step in the first point in the guideline says change to logarithmic form, which means x is equal to log base 3 of 18.381. Now, previously, we saw that there is a formula that can be used to find logarithms of all bases. This is not base 10 and not base e, so we can't just use the log button directly. We must use the ratio of the log of the argument over the log of the base. And simply putting that into the calculator, we will be able to find the answer. And I'm getting 2.649995541. So, we would probably, depending on what purpose you're using this for, round to 2 or 3 decimal places. So to round to 3 decimal places, 2.650. Okay. Now, if you wanted to check that to make sure it works, the more decimal places you put back up in here for that x, the closer you will get to 18.381. Just keep that in mind. Moving on to example number 2. So, one of the other points was, if the equation is in exponential form and the base is the unknown, take the log of both sides. Now I also realize that we could take the fourth root because b to the power of 4 equals 1,296. So we could just take the fourth root of 1,296. However, I want to look at ways to work through these when the whole situation is more complicated and a way that works in all cases. So let's look at this method of taking the log of both sides. What does that mean? And all it really means is I write log in front of both sides. Okay? And those are log base 10. So log 1,296 is a number I know I can get on the calculator. We are trying to isolate for b, right? Remember the property that goes with the exponent here, that this can also be log 1296 equals 4 times log b. And now 4 is just multiplied by log b. So in order to begin to isolate this b here, we will divide both sides by 4. And I'm not going to actually put this number on the left into my calculator just yet, because keeping it in this form is much more accurate. It might have a whole load of decimal places to it, so I find it easier to just keep it in this form. So let's see, we get this cancels here, and we get that log b equals log 1296 all divided by 4. So this is in logarithmic form, and we are trying to evaluate the argument. And notice that when the equation is in exponential form, it's solved for the argument. That means that, and we'll move up here, b, the argument, is equal to the base, which in this case is a 10 because I wrote log in front of each side. So we can make it whatever base we want. We'll use 10. To the exponent, which is everything on the other side. So log 1296 all over 4. That's the exponent. The tricky part will be trying to put this into the calculator. Remember that the second function of your log key is 10 to the x, so I would use that. And so let's see, b is going to be equal to, and I'm working on my calculator, second function log, so I get 10, and it's waiting for the exponent. In the exponent, I will just type log 1296 and divide by 4. I think it might be safe to put brackets on there. I'm getting a 6, but I want to check it with brackets, so just a moment. Second function log 10 to the power. Do a bracket log 1296, end the bracket. Now divide that by 4. And we still get 6, so 6 is correct. And I think that makes sense. If we were to check 6 to the power of 4, it's 1296. Let me make that 6 look less like a b. Okay, there you go. Moving on to another example. We have an equation in logarithmic form where the argument is the unknown. And so changing this to exponential form will help, which means y, the argument, is equal to the base raised to the exponent. That one could not have been easier. So y equals 3 to the power 5, 3 to the power 5, 243. Okay. Here we have a case of the, we have it in logarithmic form, and the unknown is the base. Let's just recall what was suggested there. I think it said change to exponential form, then take the log of both sides, right? So let's do that. I believe I'm looking at, if the equation is logarithmic form and b is the unknown, that's number 4. Change to exponential form and then take the log of both sides. You may need to convert back to exponential form again. So I'm using that one for here. So we're going to change to exponential form. That means b to the power 3 equals 64. And we're just working on this side right now. Now we'll take the log of both sides. So I'm just going to write log in front of both. Those will be log base 10 now, because I just took the log of both sides. Let's use the property for a power and move this 3 in front. So it is 3 log base b equals log 64. And with 3 multiplied by log b, we can begin to isolate that b, which is starting to isolate log b by division by 3. So log b equals log 64 divided by 3. Changing back to exponential form, the base 10 to the power log 64 over 3 equals the argument b. And so this is much like the last one. I will use my second function log button to get b, to get 10 as the base. And in the numerator, log 64 divided by 3. And the answer is 4. Pause the video and try this other one over here for yourself, following the same pattern. And then I will show the results. Okay, there you can have a look at the answer, 5.999, essentially 6. If you were to sub 6 in, you get a value that is just a little higher than 529. But it's basically 6. You can see I've followed the same pattern of changing to exponential form, taking the log of both sides, applying the property of a power, and bringing that 3.5 as a multiple in front so it can be divided out of both sides, isolating log b, and now going back to exponential form with 10 as the base to find b. Let's look at an example where logarithms are used, and that has to do with the pH of water. So H plus is a notation for the hydrogen ion concentration in water. It's an indication of the acidity or the alkalinity of the water. Neutral water has a pH of 7. So if the equation for pH is the negative log of the hydrogen ion concentration, find the hydrogen ion concentration if the pH of water is 5.6. So pH equals 5.6. So 5.6 is equal to negative log of the hydrogen ion concentration. That is the argument, right? This is a base 10. So we have a logarithmic equation where the argument is the unknown, so we'll change to exponential form. Before we can do that, we must have coefficient 1. Right now we have a coefficient of -1. So I must divide both sides by -1. And we will see that -5.6 equals log of the hydrogen ion concentration. Now we have coefficient 1, which means we can change to exponential form. The basis, or the hydrogen ion concentration, is equal to 10 to the power of -5.6. And that number is, let me get my calculator, 0. Let's count up the zeros. 1, 2, 3, 4, 5. Very small number, 2511. That is the hydrogen ion concentration. If I recall my chemistry correctly, that is in moles per liter. But that's not an issue. Don't worry about the unit. Okay. Another question involving pH is where we have to find the pH. If the hydrogen ion concentration in a sample of water is 0.000000006 mole per liter, find the pH. Well, pH equals the negative log of the hydrogen ion concentration of 0. And that was 1, 2, 3, 4, 5, 6, 7, 8 zeros. And a 6. How do we find that number? So I will just have to type that directly into the calculator. I will put in my negative log and type in 0.000000006. And the pH comes to 8.2. Here are some more examples. Let me show you those two. I would suggest pause the video and give these a try, and then compare your answers to mine. Okay, as you can see, the answers are here. We'll go in this direction, and then x equals -4. A similar process is used for the next one because it is an exponential equation. I've changed to log form. However, the base is e, right? So anytime we have log base e, we just use the ln instead of log base e. Going up to this part, divide by -3 on both sides to isolate x. Here are two more. Pause the video and try those. Okay, again, we are in exponential form for this first one up here. So we will write it in logarithmic form. I did 2 steps here on the second one. I converted the log base 6 of 0.005 to the ratio of the log of the argument over the log of the base. And I brought the 3 over because it should be subtracted on the other side to isolate x. Make sure that this is all calculated before you subtract 3 from it. If you have a problem with your calculator, that might be the issue. Do the intermediate steps. In this case, we have a logarithmic equation, and before we can change it to exponential, it must be coefficient 1, and right now it's coefficient 6. So if we divide both sides by 6, that's where I get that top line. I decided to write it as a decimal since it was as precise as -0.5. If not, leave it as a fraction. and changing to exponential form, then to isolate the argument. There is one last one for you to try here. Pause the video and give that a try. To begin solving for x in this case, I want to isolate the term or the logarithm term that has x. So since it's a negative, I thought moving it to the other side would make it positive. And therefore, the log base 2 of 45 came back over here because that's just a number. So you will see that we have also the 2 was put up as the exponent here. So log base 2 of 3 squared subtract log base 2 of 45 equals log base 2 of x. Now let's calculate the 3 squared. That's a 9. That's all that happened in that line. And since we have coefficient 1 and same base all the way through, we can combine these two into a single logarithm using the quotient rule. So we get log base 2 of 9 over 45, and that is equal to log base 2. So therefore, the arguments must be equal to each other because everything else is the same. So x equals 9 over 45, and when that is reduced, that is 1 over 5, or 0.2. Well, that's it, folks. I recommend some practice. Hope that was helpful, and thanks for watching.